Imagine trying to build this like a futuristic Megacity, but the blueprints alone cost $725 million.
Right. And there literally aren't enough architects alive to even draw them.
Exactly. Welcome to the Semiconductor Industry Today. I'm your host, and today on this deep dive, we are peering into the microscopic, just infinitely complex physical brains of our digital world.
Yeah, we're looking at a massive revolution happening right now in chip design. Because, for decades, taking an architecture from code to physical silicon was this super exclusive club.
Oh, totally locked behind corporate velvet ropes and, well, $100 million paywalls.
Spot on. But we're exploring how that entire landscape is being democratized by open source tools.
We're talking about a reality where anyone, maybe even you listening right now, could actually design your own microchips.
Which is just mind blowing.
Yeah.
And we're pulling insights from some incredible technical breakdowns today, specifically looking at the integrated circuit tape out process with open source tools.
Yeah, and we're examining the sharp divide between this new silicon democracy and traditional commercial EDA standards. Okay, let's unpack this. Because to understand the revolution, we really first have to understand the sheer mind boggling scale of the industry as it operates right now.
It really is a scale that's difficult to wrap your head around, let alone disrupt. I mean,
Yeah.
we are looking at a global machine that passed $550 billion in revenue a few years back.
And it's projected to cross the $1 trillion mark by 2030, right?
Exactly. And to understand the gravity of these open source tools, you have to look at the four major pillars that make up this whole ecosystem.
Right. So first you have the design companies. Those are the fabless players.
Yeah. The ones who write the code and draw the blueprints, but they don't actually own any manufacturing equipment. Second, you have the fabrication companies, the foundries like TSMC.
And they're the ones who actually etch those blueprints into raw silicon.
You got it. Third is the assembly, packaging, and test segment. And then finally, the equipment manufacturers building those massive, EUV lithography machines that make it all possible.
And the financial barrier to entry at just that very first pillar, the design phase, is just staggering.
Oh, it's astronomical.
Like, the sources note that if you want to design a chip using a 5 nanometer process today, the R&D and engineering hours will run you nearly $550 million.
Yeah, and if you push that to the bleeding edge, to a 2 nanometer architecture, that price tag skyrockets to around $725 million.
You are spending $750 million before a single grain of sand is ever melted down. That is just insane to me.
It really is. And the geographic and corporate concentration of where that money flows is incredibly tight. Taiwan basically dominates the foundry manufacturing.
Right, alongside heavyweights in South Korea, Japan, the US, and China.
Yeah. But beneath all that geopolitical maneuvering and those trillion-dollar projections, there is a very urgent human crisis. If we connect this to the bigger picture, the most critical bottleneck right now isn't silicon wafer supply or lithography equipment.
It's talent.
Exactly, it's talent. By 2030, the U.S. alone is facing a projected shortage of 67,000 unfilled technical, computer science, and engineering jobs in this sector.
67,000. That's like an entire city of highly specialized engineers just missing from the workforce.
Yeah, just not there.
I mean, if you're listening to this and you know hardware description languages like Verilog, the industry is basically handing out blank checks right now.
Oh, absolutely. Companies are aggressively hoarding talent with massive sign-on bonuses, university partnerships, hybrid work perks, you name it.
Because it's an unsustainable model. You just can't scale a trillion-dollar industry when the human capital required to design the product simply doesn't exist.
Right. So with blueprints costing $500 million and this massive talent drought, the industry's only survival mechanism was hyper-automation.
They had to find ways to turn code into silicon with minimal human input. And that massive gauntlet is known as the tape-out process.
Which is such a fantastic relic of a term, by the way.
Oh, tape-out. Yeah, where does that actually come from?
Historically, it literally meant the moment a team of engineers finished a design, recorded the layout data onto a massive reel of magnetic tape, and physically shipped it off to the foundry.
Wow, that's so analog for something so advanced.
Right. But today, tape out represents the final handoff. It is the culmination of this incredibly dense, automated IC design flow where a verified digital architecture is transformed into a geometric physical reality.
Okay, let's break down the mechanics of that flow because it is essentially an 11-step pipeline that translates logic into geometry.
Yeah, 11 distinct steps.
It starts with RTL synthesis, right? Taking your behavioral code and mapping it to actual logic beats. Then you move into floor planning and placement.
Which is deciding precisely where your microscopic macro blocks and standard cells will physically sit on the silicon die.
Then there's clock tree synthesis, or CTS. And finally, routing, which generates that GDSII file. Let's actually drill into clock tree synthesis because I think it perfectly illustrates the sheer complexity here.
Oh, CTS is fascinating. It's a huge hurdle.
How does CTS actually ensure the clock signal hits every single component simultaneously? Because it can't just be drawing straight lines.
It's anything but straight lines. The clock is basically the heartbeat of your chip. If a clock pulse arrives at one flip-flop, even 10 picoseconds later than it arrives at another.
That was 10 picoseconds?
Yeah, incredibly tiny fractions of a second. If that happens, the later flip-flop might sample the wrong data. That's called clock skew, and it will outright kill a processor.
So how does the automated tool fix that?
Well, during CTS, the tools map out this fractal-like network of microscopic wires to distribute the pulse. And to balance the timing, the software actively inserts physical buffers.
Meaning it puts in tiny signal amplifiers along the shorter path to intentionally slow down the signal.
Exactly.
Yeah.
It intentionally delays it, ensuring it arrives at the exact same picosecond as the signal traveling down a much longer path.
Okay, I have to challenge the premise here, though. You're talking about automating this completely. We have incredibly powerful AI and compilers today.
Sure. Yeah.
Why does this require 11 distinct, highly complex steps? Why can't a modern compiler just ingest the Verilog code, calculate the logic, and instantly output a 3D printable layout in one go?
Because you aren't just calculating logic, you are literally fighting the physical universe.
Okay, what do you mean by fighting the universe?
When you're dealing with billions of transistors on a die the size of a fingernail, you are constrained by the finite speed of light and the realities of electromagnetism. Specifically, the design flow has to constantly calculate two critical metrics for every single pathway: propagation delay and contamination delay.
Walk us through the exact physics of those delays. What causes them?
It basically comes down to resistance and capacitance, what engineers call RC delay. The microscopic metal wires connecting your transistors aren't perfect conductors. They have electrical resistance.
And because they're sandwiched so closely together on the silicon, they act as capacitors, storing electrical charge.
Spot on. So propagation delay is the maximum time it takes for a signal to fight through that resistance, charge up that capacitance, and fully stabilize at its destination.
Okay, and contamination delay.
That's the minimum time before an output even starts to change. So the software can't just, print a layout, because every single nanometer of wire you route fundamentally changes the RC delay of that specific path.
Right, so if you route a wire over another heavily active wire, the capacitive coupling changes the timing dynamically.
Exactly. That's why there are 11 iterative steps. The tools place the components, route the wires, simulate the physics, realize the timing is broken, rip up the wires, move the components, and try again.
Which perfectly explains why managing those billions of precise physical constraints requires commercial electronic design automation, or EDA software that costs tens of millions of dollars to license.
Yeah, the math is just too staggering for anything else.
But fighting that physics manually requires thousands of engineering hours. And the U.S. military needed a shortcut, didn't they?
They absolutely did. The Defense Advanced Research Projects Agency, or DARPA, recognized that relying purely on commercial EDA flows and massive teams of scarce engineers was a strategic vulnerability.
So they initiated the IDEA program because the Department of Defense needed custom systems on a chip for highly specialized, low-volume applications.
Right. Things like autonomous drone navigation or advanced radar processing. And the traditional design cycles were just taking years.
So DARPA set what sounded like a completely absurd goal. Create a general-purpose hardware compiler that could translate source code to a physical layout in under 24 hours.
With absolutely zero human intervention in the loop.
That's nuts. A literal push-button flow. You feed it code, you get a chip a day later.
Exactly.
Here's where it gets really interesting. This DARPA initiative gave birth to a project that ultimately led to OpenLane.
Yeah, OpenLane is incredible. It's the open source EDA tool that created what we call the single file revolution.
So instead of needing a massive team of specialized engineers manually tweaking the floor planning, the CTS buffering, and the RC delays across 11 different proprietary software suites.
OpenLane uses one single configuration file, just a JSON or TCL file, to completely orchestrate the entire journey from code to the final GDSII layout.
Just one file? That's amazing.
It is. It's a masterful orchestration of several underlying open source tools programs like Yosis for synthesis, OpenRoad for the placement and routing, and Magic for layout viewing. OpenLane acts as the master conductor.
But it's vital to understand that OpenLane couldn't orchestrate anything without a parallel revolution that happened at the same time, right? The
Yeah.
release of open source process design kits, or PDKs.
Yes, the PDKs.
Mm.
Without those, OpenLane is just software with no hardware to run on.
They're essentially the physical rulebooks. Explain how a PDK bridges the gap between the OpenLane software and the actual foundry.
Well, a PDK contains the exact physical and electrical constraints of a specific foundry's manufacturing equipment. It tells OpenLane precisely how thick a metal layer can be.
Or like the minimum spacing between two wires before electrons start jumping the gap.
Exactly. And the exact resistance and capacitance values of the transistors they manufacture. Historically, foundries guarded these PDKs like nuclear launch codes.
Right, you had to sign ironclad NDAs just to even look at them.
Yeah, but then Google sponsored Skywater Technology to release the SKY130 PDK, a 130 nanometer process, completely open source on GitHub.
And then Global Foundries followed suit with the GF180 MCU PDK. Suddenly, the open source software had real-world physics to compile against.
And Google didn't just release the rulebook, they sponsored multi-project wafer, or MPW runs.
Meaning they actually allowed developers to submit their OpenLane designs, and Google footed the bill to have them physically fabricated on real silicon wafers.
Yeah. In traditional manufacturing, just buying the mask set for a 130 nanometer chip
Yeah.
would cost a startup tens of thousands of dollars.
Yeah.
Google made it completely free.
It was an unprecedented democratization of hardware. Anyone with an internet connection could theoretically design a bespoke microcontroller, run it through OpenLane, and get physical silicon mailed to their door.
Exactly.
But I need to push back on this because it sounds almost too utopian.
Okay, how so?
You're talking about completely automating this process with a free JSON file. But if timing delays are as hypersensitive to physics as you just explained,
They are?
if we're dealing with microscopic capacitance, resistance, and nanometer level clock skew, how can a generic open source tool possibly account for the microscopic physical variations that a team of 50 senior engineers at Apple would manually tune?
Right.
Why is anyone still paying millions for commercial EDA if OpenLane is free and automated?
That is the defining tension of this entire movement. And the reality check is that the commercial EDA giants companies like Cadence, Synopsys, and Siemens use proprietary heuristic algorithms that have been refined over 40 years.
So they're just unmatched when it comes to optimization.
Absolutely unmatched when it comes to PPA, power, performance, and area. If an Apple engineer is trying to squeeze an extra 500 megahertz out of a mobile processor while shrinking the silicon footprint to save millions in manufacturing costs, they need that granular manual control.
So OpenLane has to leave performance on the table to achieve that zero human intervention automation.
Exactly. Because OpenLane is designed to succeed without human help, it uses highly conservative margins. It spaces wires further apart to avoid capacitive coupling.
Oh, I see. And it uses larger, safer logic cells to guarantee timing is met.
Right, which bloats the overall size of the design and increases power consumption. Furthermore, the open source PDKs currently available are limited to mature, larger nodes like 130 nanometer or 180 nanometer. You cannot use OpenLane today to design a 3 nanometer chip.
Which makes sense. This raises an important question, though. What is the actual purpose of your design?
Precisely. If you are building the next flagship smartphone, you have to use commercial tools.
Right.
But if you were a biomedical startup prototyping a custom sensor interface, or an academic researcher testing a radical new RISC-V architecture, or a student just trying to understand how RC delay works in practice, OpenLane is a miracle.
Because it removes the financial barrier to innovation entirely. You don't need venture capital just to see if your architecture functions.
Exactly.
Let's bring this down to the actual engineering level in practice. Let's look at how you'd actually build something complex, like an arithmetic logic unit or ALU, using these tools.
Okay.
The sources heavily emphasize the use of macro cells. Now, for anyone who has ever built complex software, using standard cells is like writing an operating system in raw assembly code, painstakingly dealing with individual logic gates.
Oh, totally.
But using a macro is like trying to drop a precompiled software binary directly into your custom operating system. It's a pre-hardened block of logic, like an adder or a shifter.
That software binary analogy is spot on. You know the exact footprint of the macro, and you know exactly how it behaves.
Right.
But just like dropping a binary into a custom OS, the memory pointers and system dependencies have to map perfectly, or you get a kernel panic. In chip design, that critical dependency is the power delivery network, or PDN.
Ah, the power grid. When you drop a macro into a core design in OpenLane, how do you actually ensure it gets power without shorting out the surrounding logic?
It comes down to vertical routing constraints. Chips are three-dimensional. They have multiple layers of metal routing stacked on top of the silicon.
Okay.
The SKY130 process, for example, has 5 discrete layers of metal. When OpenLane integrates a macro, you have to be incredibly strict about which metal layers the macro is allowed to use.
So you might configure your JSON file to restrict the macro to only route its internal signals on, say, metal layers 1 through 4, leaving the top layer, metal layer 5, completely empty.
Right. You reserve metal layer 5 for the core's macro-level power grid. That top layer acts as the main voltage and ground highways, dropping vias, which are vertical connections, down into the macro to power it.
So what happens if you misconfigure the PDN in your OpenLane setup and accidentally allow the macro to block layer 5?
You get what's called an IR drop. The resistance becomes too high, the voltage drops from 1.8 volts down to maybe 1.6 volts, the transistors slow down, the contamination delay changes, and the chip is basically dead on arrival.
Wow. It's an incredibly delicate balancing act. And that sensitivity just goes into overdrive when we look at memory, doesn't it?
Oh yeah.
The architecture of SRAM static random access memory is famously difficult for automated tools to handle.
SRAM is the ultimate test of physical layout. A standard SRAM cell uses 6 transistors arranged in a cross-coupled inverter loop, and they are hypersensitive to leakage current and electrical noise.
Meaning, if the physical layout of those 6 transistors isn't perfectly symmetrical and balanced, a tiny fluctuation in voltage from a neighboring wire can cause the cell to flip its state.
Exactly. A binary 1 becomes a 0 simply due to proximity noise.
Which means automated placement tools, which just scatter cells wherever they fit to optimize routing, would just destroy the memory integrity.
They absolutely would. Standard automated tools cannot be trusted to lay out individual SRAM transistors. They require painstaking manual layout tuning by specialized memory engineers.
But wait, to bridge this gap for the open source community, we now have tools like OpenRAM, right?
Yes, OpenRAM functions as an open source memory compiler. It contains those perfectly tuned, human-verified SRAM layouts and generates customized memory blocks that you can then import into OpenLane as hardened macros.
It abstracts all that hypersensitive physics away from the user.
Exactly. It handles the terrifying physics so you can focus on the logic.
Well, we have covered massive ground here today. I mean, we've gone from the macroeconomics of a $550 billion industry desperately hoarding talent down into the microscopic physics of RC delays, clock buffering, and 5-layer metal power grids.
It's a lot to process.
It is. And we've witnessed how DARPA, Google, and the open source community engineered the single file revolution of OpenLane to literally tear down the velvet ropes of hardware design. Okay, so what does this all mean?
Yeah.
It means the fundamental power to create the physical brains of our digital world is shifting. It's moving out of the exclusive control of a few mega corporations and into the hands of a global collaborative community.
And if you step back, there is a profound historical parallel here. Decades ago, software had its Linux moment. Operating systems used to be strictly proprietary, insanely expensive, and completely locked down by massive tech giants.
Right.
But the open source Linux kernel proved that a decentralized global community could collaboratively build an architecture that would eventually power the vast majority of the internet, enterprise servers, and mobile devices.
Which is exactly what we're seeing start to happen with Silicon.
Right. As these open source hardware tools advance, as they inevitably push beyond 130 nanometer nodes, optimize their heuristics, and begin encroaching on cutting-edge territory, are we standing on the exact precipice of the Linux moment for physical silicon?
Oh, wow.
Will the device you're listening to this deep dive on someday be powered by a processor designed not by a single corporation, but collaboratively by the internet?
That is an incredible thought to leave on. The idea that the ultimate black box of technology, the silicon processor itself, is suddenly something anyone can peer into, tinker with, and compile right from their laptop, it changes the entire landscape of what is possible. Thank you for taking this deep dive with us today.